Yeah, I'd like to first thank the organizer of this workshop. And we had a lot of theory discussion yesterday, and we just have Ashvin telling us, a nice story of anomalous crystal. Okay, so I'm going to talk about the experimental aspect, and I hope I can entertain you from the experimental point of view, like why did we even start to look at something like 5-layer graphene by skipping the 1, 2, 3, 4, okay? So I'm going to talk about the integer and the fractional quantum anomalous Hall effect in rhombohedral graphene. Anomalous means zero magnetic field. And before I really talk about the anomalous version, I want to just briefly review the non-anomalous, right? The integer and the fractional quantum Hall at high magnetic field. So the integer quantum Hall happens when you have two-dimensional electron gas subject to a high magnetic field. When the mobility is high enough, you get steps in this Hall resistance that's precisely quantized at h over e squared divided by an integer I here. And there's a very nice way of visualizing this effect, that you have integer number of states, chiral state winding around the edge of the 2D flakes. And that is this I is basically determined by the number of channels you have there. And this is like a single particle picture, and it works pretty well without considering electron-electron interaction. And when you introduce the interactions between electrons, you have both the topology and the correlation at the same time. Experimentally, what you get from even higher mobility two-dimensional electron gas is not only you have plateaus of the Hall resistance at the integer values, but you also have this little plateaus correspond to h over e squared divided by a fractional number, and that fractional number corresponds to the filling factor of the lambda level, right? So basically, you need flat band to promote the correlation effect, and you need interaction to gap out the ground state at the fractional filling factors. And you probably know this better than I do. Once you have this kind of fractional quantized ground states, you are going to have many beautiful physics where the excitation carries fractional charge, they obey fractional statistics, and some of these anyons obey non-abelian statistics. You can do braiding, for topological quantum computation. But from the experimental point of view, it is nice to have all those at, say 25 Tesla, but wouldn't it be nice to completely eliminate the magnetic field and realize something like this at a zero magnetic field? Okay, so that has been a question, and it turns out, condensed matter knows where to, what to make use of to get such kind of integer and fractional quantum Hall state at the zero magnetic field. This, anomalous velocity was well known, for all the condensed matter physicists, that there's something called a barrier curvature. It serves as kind of like an intrinsic magnetic field that deflects the electrons to the transverse direction. And experimentally, you can really pick it up by just measuring the Hall resistance at the zero magnetic field, right? It's a summation of the barrier curvature, and you get the Rxy at the zero magnetic field. And when you have a band that's completely filled, like in the case of lambda levels, you have a Chern number, which is an integer number, 2 pi, the integration of barrier curvature divided by 2 pi. And this is a TKAM picture to look at the integer quantum Hall effect. So, clearly there's something that you can make use of. Instead of the external magnetic field, you can just use the intrinsic external magnetic field to assemble quantum Hall state at zero magnetic field, right? And then there's a Haldane model that basically give you a specific model with hopping parameters assigned to electrons on this graphene lattice that essentially can realize the zero field quantum Hall effect. Experimentally, it was first observed in magnetic TI, okay, magnetic doped TI at like tens of millikelvin temperature. You got the Hall resistance quantized at h over e squared. In other words, this is a Chern number equals 1 quantum anomalous Hall effect. And after that, there has been several material systems where people observe similar, like h over e squared Hall resistance at the zero magnetic field. They all have Chern number equals 1. Okay, I'm going to get back to this point later. So this is the integer version, and this doesn't really need a flat band. although some of the system that does emerge from flat band, but the integer version in principle does not need flat band. Well, when you want to assemble the fractional Chern insulator or fractional quantum anomalous Hall effect, theorists has been thinking about, like, first, is it possible to have such kind of state? Second, what is needed? Without talking about any specific material system, there is some kind of idea of how to engineer such effect in crystals, okay? Basically, you can think of it as like, we're just mimicking Landau levels because we've got fraction there once, and then let's just mimic it, right? Landau levels is very flat to promote the correlation effect. Landau level is topological. Every Landau level has a Chern number 1, and the Landau levels are well separated by the cyclotron energy. So, the theorists were thinking, okay, so if you come up with an atomic crystal that mimics this 3 aspect, maybe you have a chance to get a fractional quantum Hall effect at 0 magnetic field, right? Of course, they later realized there's other, conditions, probably like ideal quantum geometry and those things. But I'm an experimentalist. I just look at things that's easy to think of, right? For example, if you have a crystal that has very flat band, right, then that will promote correlation effect when you put charges in that band. And then you want your band to be topological, just to look at Landau levels, and that's how you can possibly break time versus symmetry. And when in atomic crystals, very often you just have 2 pair of bands that have opposite Chern number, and they always cancel each other to give you a 0, anomalous Hall signal. But you can make use of the exchange energy to split them up, and then you just put in the right number of electrons and leave one band to be empty. Then you pick up the Chern number of that occupied band, right? So in this case, the time versus symmetry is spontaneously broken instead of explicitly by a magnetic field. Okay, so it is possible, but nobody knows which material system to look for such kind of thing in. And as an experimentalist, and that is a question I think more, and I'm going to tell you, a crystalline form of graphene, no twisting between layers, just part of graphite, is the right thing to look at, okay? And I'm going to make it more, put more flavor into it by putting something else next to the 5-layer graphene. The first example I'm going to show you is to put the WS2 layer, which is a transition metal dicharcogen line, has strong spin-off coupling. And then to realize the fractional quantum anomalous Hall, I'm going to introduce the moire, as Ashwin has already told you. Okay, so let's take it step by step. I think it's fair to say that even in 2024, we don't even really understand what graphite does. Okay, I think that's a fair statement. If you just use tape to exfoliate graphene, you randomly get different thickness, and this color contrast with the substrate tell you the layer number, okay? And the contrast is linearly proportional to the layer numbers. For example, here is a piece that we determined to be like 5-layer thick. Well, it turns out the structure is more rich than just having different layer numbers, because if you use a different way of looking at the same flake, instead of using visible light from the optical microscope, use some infrared light that's much lower energy, you are going to see richer structure in this region of 5-layer graphene that seems to be homogeneous under our visible eyes. Infrared light tell you, oh, there are domains in there that's bright and dark, okay, within the same region.
Are they both 5-layer?
Yes, these 2 regions are both 5 layers. So this one is tetra layer, and you can tell the contrast between tetra and the penta from the visible channel. But you can't tell the difference between 5-layer Bernal and 5-layer rhombohedral from the visible. Yeah. And these are 2 different stacking orders of graphite, right? And specifically, the Bernal stacking corresponds to the so-called AB, AB, AB stacking. There are just 2 positions when you stack layers on top of each other. All the even layers are aligned. If you look from the top, all the layers are aligned, but they are shifted. Well, there's another stacking order that we also got from here. It's called the rhombohedral stacking order, which is the so-called ABC, ABC, ABC stacking. And that is corresponding to when you stack layers on top of what's existing there, you keep shifting in the same direction, okay? And then you got the rhombohedral. So Bernal stacking is more stable than rhombohedral. Bernal is roughly 80% of graphite is in Bernal. And the rhombohedral is like a metastable state, something like 10% of graphite. But it's there, okay? So it's a local minimum, it's allowed to exist. And if you manage to stabilize rhombohedral, there's good experiment you can do. But just one more word. The reason that you can use infrared light to visualize this the stacking order is because the stacking order affects the low energy band structure much more than it affects the high energy. So visible photon is not as sensitive as infrared photon to the stacking order, okay? And the reason that you want to look at the rhombohedral graphene is because it gives you a very interesting energy dispersion relation. As Ashwin told you, you have this staircase structure, and most of the electron from this intermediate orbital, they just hybridize very strongly and push themselves away from zero energy, and only a pair of dangling bonds are left at zero energy, and they remain degenerate. So if you think of, the low energy physics is only residing here and here, they talk to each other very indirectly, right? They have to hop through all the layers, and that results in dispersion that's roughly momentum to the nth order, where n is a layer number, okay? To the zeroth order, neglecting other smaller hopping parameters. And this tells you that if you have monolar graphene, you get the famous linear Dirac band, very big Fermi velocity, has nothing to do with flat band at all. But if you crank up the layer number to 2 layers, 3 layer, 4 layer, 5 layer, very quickly you can notice that at the neighborhood of zero energy, this band becomes more and more flat. When you get to something like 5 layer, although this is not parabolic band at all, but if you put a parabolic band there and compare the density states in the range of, say, 5 millieV, you can actually tell the band here is already so flat, it's comparable to effective electron mass of something like bare electron mass, okay? And then, basically, I'm saying if you just isolate part of graphite, if you have the IRIs, you isolate it, you get flat band automatically. You don't need twisting, you don't need Moiré engineering, nothing, not even gating. This is the first type of flat band that you can get from rhombohedral graphene, and we'll call them as pristine flat band. And this structure has another advantage that makes it even more interesting, that you can use the gate electric field to build a potential difference between the top layer and the bottom layer. And then you break the symmetry between this A1 and the Bn. That translates into a gap opened at the Dirac point. And it can squeeze the bottom of the conduction band bottom and make it even more flat, even bigger density states, right? So there's also tunability. Yes?
But when you apply the field, you can even, like Bernal, make open up a gap and so pretty flat. Right?
Yeah, but now, okay, so even on the odd layer has slight difference, but if it's odd layer, there's always a Dirac cone there, right? That's annoying. You want to get rid of that. The even layer is more complicated, but not as flat as here. Yeah. Yes?
And n equal to 5 is just the largest you ever get to see, or there's another instance?
No, we tried 6, and I think Guy's group probably tried something like 10 layer, 11 layers. But it's not the flatter the better, okay? I mean, sorry, it's not the thicker the more flat it is. Because as you can see already here that, it doesn't follow k to the 5th perfectly. There's this up and down due to the so-called trigonal warping terms. And those things will increase as you go thicker. So it is possible that there is a sweet spot in the middle, and maybe 5 layers is a sweet spot. Okay, it's just a tight banding calculation. That's all what I know how to do, okay? Anyway, so there's flat band. So it's possible to have correlation effect, showing up here. And there's another, advantage of this system is that it could also be topological, because these band crossing points, they carry big barrier phase, right? Monolar graphene has a barrier phase of pi per valley per spin. Or 5-layer graphene, the pseudo spin winds 5 times faster than monolar graphene, so it has a 5 pi per valley per spin. In the pristine form, again, if you use electric field to gap out the band structure, you can control the distribution of barrier curvature on the states near the band edge. And if you just look at a fixed electric field, K and K prime valley, they always have opposite barrier curvature, the time versal pairs of each other, right? And if they're equally populated, there's zero anomalous Hall. And if you just look at a single valley, and you can change the sign of the gap by just change the direction of your electric field. You can induce a topological phase transition and change the color of your Berry curvature distribution there. Okay, so this is basically why we, as experimentalists, want to study rhombohedral 5-layer graphene in the very first place. Okay, at that point, nobody tells, oh, you can get integral or fractional quantum Hall, but we just think flat band plus big Berry curvature could result in something interesting. Okay, and if you manage to make, stabilize the rhombohedral stacking order in your device, you can make a Hall bar device, measure longitudinal transverse resistance, and gate it by the top piece of graphite and bottom piece of graphite gate. And you can control two parameters independently experimentally. One is called charge density. The other is called the gate electric field that you can use to open up the gap. Okay. This is the first view. This is crystalline 5-layer graphene. There's no moire, no TMD, nothing, the simplest form. And you are just measuring the resistance at the temperature of hundreds of millikelvin. Okay. And it apparently is already more rich than what you expect from a gap-opened semiconductor. So let me point to you several things. At the 0 displacement field, 0 charge density, as if you are doing nothing using your gate, the band structure calculation tell you there's a big density state, so you think it may be a very good metal, but the experiment tell you it's a very, very good insulator here. Okay, that tell you the band is so flat, it's already gap out at the 0 energy. And then you can do two things. One is to keep it at charge neutral and increase the displacement field by gate. You see, you get out of this correlated insulator region, you get into some metal, and then possibly the band insulator, because when the potential is big enough, that's going to dominate over everything. Right? You have this transition. And you can also put charges into this, this 5-layer graphene, and you got different regions that's separated by colors, phase boundaries. I'm not going to dive into what those are, but in simple picture, remember you have spin degree of freedom, you have valley degree of freedom, so every band in principle has 4 copies. But when you have flat band, the exchange interaction could break some of the symmetry, either spin or valley or combination of spin and valley, and that's what these states are. I labeled them here. And some of these states, for example, here at the high displacement field, actually has been seen in ABC trilayer graphene by Andrea here. The pentalayer graphene give you new states at the 0 displacement field because trilayer is not yet flat enough at the small displacement field. But when you go to high displacement field, they share a lot of common features. Okay. So I hope this has convinced you that even the crystalline 5-layer rhombohedral graphene already show signatures of electron correlation and symmetry breaking. Now let's add some flavor to it, okay? So the first thing that we did is to think about what graphene does not have, okay? Graphene does not have strong spin-off coupling. So let's borrow some spin-off coupling from a TMD layer. So we make another device, which is 5-layer rhombohedral graphene neighbored by a monolayer tungsten disulfide, which has strong spin-off coupling. And through the proximity effect now, graphene electron has some spin-off coupling in it, maybe on the order of 1 to 2 milli-electron volt. And on the other side of the graphene, we purposely twist away from 0 degrees, so you can think of the moire effect between the bottom layer graphene and the bottom HB is negligible. It's not there, okay? And experimentally, we do the same trick. We scan charge density, we scan the gate displacement field, and we measure the anomalous Hall resistance and the longitudinal resistance at the same time. What's interesting is, in part of the phase diagram that's located at the charge neutrality, 0 charge density, and a range of gate displacement field, you suddenly have a lot of very well-defined anomalous Hall signal, a few kilo ohm level. At the same time, your longitudinal resistance literally just vanish, okay? It feels like something topological there. And if you park at the middle of this region and sweep your magnetic field, the vertical magnetic field back and forth, you're going to get this kind of magnetic hysteresis where the Rxy is quantized at h/5e². Remember that integer tells you how many channels you have on the edge. h/5e² tells you it's a Chern number equals 5 state. So experimentally, it's pretty clear this is an integer quantum anomalous Hall effect. And it has the biggest Chern number than any other integer quantum Hall material that you have seen. And this 5 just comes from the fact that the pseudospin winds 5 times faster, and there's a Berry phase of 5 pi. Okay, but this is, experimental driven. There's no theory prediction of it. And we were trying to understand what's going on just to compare this C equals 5 quantum Anomalous law with other quantum Anomalous law that has been seen. It's clearly different from the magnetic TI things because we have no magnetic element here. Clearly, it has nothing to do with ordering of spins. It's also very different from the quantum anomalous law you get from the Maury superlattice of 2D materials, like graphene aligned with HBN, like Andrea did, or TMD. Phenomenologically, if you have Maury and you can have the time ratio pairs to be in the K and the K prime valley, and when the band is flat enough, you put in the right amount of charge to occupy just one valley. Okay, it's not at the charge neutrality. It's at the charge density correspond to Maury fitting factor of, let's say, 1. And then you can collect the Chern number of that occupied band. Well, remember, in our case, this state is residing at charge neutrality, and it's clearly different from Maury, and we know there's no Maury. So there's only one way out, is that you have to equally populate the two valleys, but instead of canceling each other, the two valleys add up in the sense of Chern number and give you a C equals 5. And this is essentially what Haldane was proposing, right? Remember, the Haldane model relies on the fact that the two valleys have opposite gap. One of the gap is inverted, so the barrier curvature change sign, and that is how the two valleys can add up, okay? That's what we think is going on here, although theoretically, there's no good understanding yet. But, this is more involved in understanding how this works. If you have the patience, I'm going to walk through this, but please stay with me. It's a bit involved. It has a lot to do with this correlated insulator at the D equals 0. Okay, that spontaneous gap out state. And we think it may be the so-called layer anti-ferromagnetic state in the sense that electron spin, no matter which valley it is in, has a layer preference. Okay, spin up is in the top layer, spin down is in the bottom layer. Neglect the 3 layers in the middle. They are not relevant for low energy physics. If you start with this state, you got a Chern number distribution like this. I mean, valley projected Chern number, okay? All the 4 bands of spin and the valley are gapped out, but they are gapped out in different ways. For spin up bands, the occupied state, the valence band is in the top layer, and the unoccupied state is in the bottom layer. For the spin down bands, it's the opposite, right? So now you can apply a gate displacement field and introduce an interlayer potential. That potential will lower the energy of all the bands that's residing at the bottom layer, these 4, so they are lowered, and promote the energy of all the bands that's located at the top layer. Another way of looking at this is that now the gap for the spin up copies becomes smaller than the spin down copies, so we can temporarily forget about the spin down copies of the bands when counting the Chern number, okay? But we still get the 0 because these two valleys will cancel each other. The time ratio, not exactly time ratio, they have the same spin, but they will cancel each other. And that's exactly why we need WS2, which will introduce the icing spin-optic coupling effect that breaks the degeneracy between K up and K prime up, give them different size of the band gap. Then you fine-tune your displacement field. You can eventually invert one of the band gap while the other band gap is still left the same way. So when you invert it, the barrier curvature change color and Chern number change sign, and that's how you get C equals 5. We think this is what's going on based on our experimental data. That's why you have a phase transition from correlated insulator to some semi-metal to this quantum anomalous law to another semi-metal to band insulator. Okay, but again, this is to be checked by theory. There's no prediction. Okay? So now I'm going to make it more interesting by showing you how we can get the fractions. For fractions, we don't need spin-off coupling, but we do need Maury. Okay? Very brief review of Maury. When you put 2 layers of 2D material on top of each other, for example, graphene and HBN, they have slightly different lattice constant, about 2% lattice mismatch, which means you get a Maury superlattice in real space on the order of 10, 15 nanometers. Of course, you can further control that by twisting the angle between them and change the periodicity. Right? This is the most general setting of Maury superlattice, called hetero-Maury. Of course, you can simplify it by making the 2 layers the same as graphene. But the important thing is Moray gives you a chance to control the kinetic energy or the flatness of your band, as well as the Coulomb repulsion energy in your system. And there's a good reason to believe Moray is a good place to look for the physics of lambda level and mimic lambda level. And since we have talked about the band dispersion of k to the nth order here, let's start with this, okay? It is partially flat. It's pretty flat at the bottom, but it's connected to this very dispersive part of the band as well. Well, first thing you can do is to put it on Moray with HBN, and then you can isolate some of your band from the more dispersive part. And you can further make this flat part even more flat by opening up the gap. Right now, you have something that looks like a lambda level. And as we talk about, when you gap it out, you have big barrier curvatures around the state. So this band could be topological. Why this is a better place than atomic crystal to realize the quantum anomalous Hall or a fractional quantum anomalous Hall or fractional Chern suitor is because it's really hard to get a crystal that's just flat everywhere across the Brillouin zone. There's a lot of density states, density electron, but it's much easier to satisfy that flat band condition in the Moray mini band. It is much less density and it's easier to control. In other words, you don't have to have the band to be flat everywhere across the Brillouin zone. You just need it to be partially flat, and the Moray serves as a pair of scissors to cut it out, and that looks like lambda level. Okay, so this is a naive picture, and the experiment we did was, as shown here. We have the Moray between the topmost layer of graphene and the top HBN, and the other side we have some angle that's, allow us to forget about the Moray effect on this side. And experimentally, you can create a flat band by opening up the gap. Now you have two options. One is to open the gap, using electric field upward. The other is electric field downward, right? The difference is you're going to push these electrons in the flat band either to be right next to the Moray or very far away from the Moray. And guess which side gives you the fractional state? As Ashwin told you, it's when the electrons are in the remote layer from the Moray when we get the weird things, okay? So this is a recap, of the paper. The low density side is very, very insulating. It's continuous range of charge density, so we think this may be a Wigner crystal. And the higher density part has, features a filling factor 1 electron per Moray and some fractional value of that. And the integer one is very well defined, okay? Rxy at h over e squared, Rxx goes to a field ohm noise level. So there's no question about the integer one. Everything looks as good as integer quantum Hall and persists to almost 2 Kelvin. The fractional ones, so far we have 6 fractional states, 3 of them above half filling, 3 below half filling, and every plateau in Rxy corresponds to a dip in the longitudinal resistance. All these states follow the so-called the Jane sequence. They're all odd denominators, and these can persist to something like 400, 500 millikelvin. They are all gap state. And at half filling, you see it just varies linearly, and it has Rxy has a value of roughly 2h over e squared, and there's no dip in Rxx. So finally, I'm showing you something that's gapless, okay, for the theme of this workshop. We don't know why. There's no magnetic field. We don't know why there's a composite Fermi liquid, but it looks like composite Fermi liquid. Okay, so here are the puzzles, right? And this has been, partially conveyed by Ashwin. That on one hand, how do these electrons in this flat band even feel the Moray potential if they are so far away? Second is, even if there's a weak Moray potential, if you look at how flat the band is and how big the mini Brillouin zone corresponding to the Moray is, if you do the band folding into the mini Brillouin zone, you will have several bands that's all entangled together. Doesn't look like a lambda level at all, right? So at this moment, there's been a lot of debates between the theorists, like what's really going on here. One of the picture is an anomalous Hall crystal, as we heard from Ashwin. We're working very hard to see if that's true experimentally. And comparing to the other system, the twisted MOT2 that Jiaqi is going to tell you about in next talk, graphene is very different. Okay, MOT2 have very strong spin-off coupling. Twisted MOT2 have the so-called layer pseudospin. The pseudospin skyrmion in real space, the immersion magnetic field thing. Well, graphene doesn't have any of those. So we have two systems that looks very differently, but they share a lot of common properties just at the experimental level. Okay? So this is probably the last thing I want to show you. Everything I'm telling you so far can be thought of as a zero magnetic field version of fractional and the integer quantum Hall effect. Well, there is opportunity here that you can go beyond the lambda levels, right? You can have Chern number higher than 1 in the topological flat band. And indeed, experimentally, we have found one example of the high Chern number topological flat band. This happens in the 4-layer rhombohedral graphene HBM array. This is on the whole doping side, okay, instead of electron dope side. This is the whole doping side at a very low displacement field. You have something here at the filling factor -1, one hole per moire. And it turns out that state here is an integer quantum Mom's Hall with Chern number equals 4. Rxy is h over 4 e squared. And there's something at filling factor roughly -2.5, clearly anomalous Hall, small Rxx. You may think, okay, so this is fractionalization of the high Chern number topological flat band. Well, at this moment, it's quite confusing because on one hand, the Rxy seems to be quantized at something like h over 3 e squared, suggesting a Chern number 3. Already, Rxx is very small. But if you check the strata formula, the slope in the Landau fan versus magnetic field has a much bigger slope than that, something like 7 or 8. Okay? We don't know why there's a mismatch like this. We just have no idea. Anyway, there is high Chern number topological flat band. That's the key message. Okay? And of course, we're talking about graphene, right? Andrea showed you can have superconductivity in tri-layer graphene, bi-layer graphene. We think there should also be superconductivity in 4-layer, 5-layer, 6 layers. If you have both fraction and superconductivity, you can start to engineer parafermions. That was hard to do previously with the magnetic field version because that kills superconductivity. And indeed, we have got superconductivity in tri-layer graphene at least. There are new superconducting states induced by TMD and things. I think Andrea probably has similar result. With that, I will just finish my talk, and these are some possibilities we are thinking of doing based on this rhombohedral crystal graphene. And thank you for your attention. I'll acknowledge my folks. Yes.
Can you say a little more about this superconducting tri-layer graphene? That new results?
Oh, that's new. I mean, Andrea talked about it in the March meeting.
Oh, I see.
I don't think he showed SC3 there, but I think he has it now. That these two states are sort of like really induced by the spin-off coupling from the TMD layer. At the same time, we also observed that there used to be an SC1, a very long stripe here at the temperature of something 100 millikelvin. In our device, when the SOC is strong enough, this thing got killed. So it's a mixed role, what SOC is doing to graphene superconductivity.
But do you have a time work breaking in those states?
You mean these states? Okay, they reside on the boundaries of different isospin symmetric breaking state. I don't think these two are like spin triplet.
So since your system borrowed the spin orbit coupling from TMD layer, right? So is it possible that you can also see quantum spin Hall effect in your system?
Okay, you notice that I put TMD on both sides at 180 degrees from each other. So we were designing this to look for quantum spin Hall at the charge neutrality, but we don't have it yet.
Okay.
Superconductivity is a kind of byproduct of that effort.
Okay, so you tried, but actually haven't.
I tried, it's not quantized.
Okay.
So there may be something there, we just need to work harder on experiment. Yeah.
For the pentalayer, yes. When you apply the displacement field in the other direction, what happens then? It's just an insulator at commensurate filling, but it's not topological, or
yeah, so you see this resistance peak happens at the integer filling factor 1, 2, 3, 4, right? They are topologically trivial. Mm-hmm. They're topologically trivial. Between 0 and 1, there may be charge density wave at smaller, fractional filling factors, but there's no time symmetry breaking at the 0 magnetic field.
Thank you.
Yeah.
So for the case of where you have Moire potential at the bottom and you feel it at the top, is it possible that the Moire potential generates some kind of charge density wave in the bottom layer, and that by Coulomb interaction produces charge density waves in adjacent layers, giving you the...
Yeah, I think that's possible. That's a view taken by some of the theory authors.
Okay.
Yeah. Yes.
It's somewhat off the main subject of your talk, but you mentioned that 80% of natural graphite is Bernal and 20 is rhomboedral. So what does it mean? If I buy a piece of HOPG, is it like 80% of Bernal stacking in a given sample? Or if I buy 100 samples, 80 of them will be Bernal and 20 of them will be rhomboedral?
So it's statistically 80% of the volume is Bernal.
In any given sample?
It could be random. You could have a flake that's purely Bernal or purely rhombohedral, a mixture of them. It could be, more complicated than that too. Yeah. And there are other stacking orders, right? You have A, B, C, B, A, B, A, B, C, B, A, something like in between. But these two are the two leading stacking orders. Yes.
I think I might have asked you this before, but is there a way to do surface acoustic wave experiments?
Possible, but I think the fact that you already have a moire here, because what you want to do is surface acoustic waves to break the transition symmetry, right? And maybe enable some modes.
Well, I think you kind of want to probe the density response function, right, at some small frequency and see whether you have this composite fermion liquid, whether there's kind of some dissipation due to the composite fermion liquid.
I think there are definitely a lot of things we know could be done to directly show the composite fermion liquid, and that is one way.
Because the geometric resonance is the other.
Yeah, so I mean, I think Liang Fu already have paper talking about the commensurate, between the moire and the Fermi wave vector composite Fermi liquid, the so-called Weiss oscillation, if you do transport. I don't think we have that now.
You mean you don't see it?
We don't see other features, features other than these fractional states.
Yeah, I see. Thank you.
But I should say this was taken. Now we think the electronic temperature probably on the order of 300 millikelvin or even higher, and now we can probably go to even lower temperature.
So for the anomalous Hall crystal, is it possible to do the nonlinear IV, study a nonlinear IV and maybe noise to reveal the
I think that's possible. So there are two things, right? One is, whether this state here is due to an anomalous Hall crystal, and you can do all those things that you suggest. I mean, we have nonlinear IV here in the real Wigner crystal topological trivial state. We don't yet have nonlinear IV here, but I think really what needs to be done experimentally is to grab a sample that doesn't have moire, and see if the impurities can ping. Because when you have moire, there's always a difficulty of differentiating that, from other pictures. Yeah.
All right. Thank you so much.
Thank you.
Wonderful talk.
Yeah.